All right, let's look at some more areas. I got pictures, I got functions. We're going to just get a bunch of areas. So this one says the integral from 1 to 4 of 1 over x dx. What do you think is the antiderivative for 1 over x? Think about it. What do you think it is? Derivative of ln x is 1 over x. Therefore, the antiderivative of 1 over x is ln x. All right? But here's a funny thing about ln x being the antiderivative of 1 over x. The derivative of the ln of the absolute value of x is also 1 over x. So to get a more general antiderivative, which we will sometimes need, we're always going to say the antiderivative of 1 over x is ln of the absolute value of x from 1 to 4. And then sometimes that will matter and sometimes it won't. In this case, it doesn't because all my numbers are positive. So I'm going to have ln of, so technically it's ln of the absolute value of 4, that's plugging my top, minus ln of the absolute value of 1. So that is the same as the ln of 4 minus ln of 1. We know ln of 1 is 0, so that area is ln 4. So this is the first one that sort of makes sense in the sense that I don't expect to get rational values for these areas. They look pretty irrational to me. You know, what is ln 4 as a decimal? It's 1.38629. That's what this area is. All right? So it kind of makes sense if you think about it. It's a little over 1. So 1 to 4, it's 1 over x. All right? 1 over x squared holds more tightly to the x-axis. We're going to expect a smaller area. But how am I going to get a antiderivative for 1 over x squared? Well, you do the same thing for antiderivatives that you do for derivatives, which is if I have a denominator, if I have x in the denominator, I'm going to make that into a negative exponent. All right. So then I can apply my power rule, raise the exponent 1, get x to the negative 1, divide by the new exponent, negative 1, and I'm going 1 to 4. All right. So I can think of that as being negative 1 over x. All right, and negative x to the negative 1 from 1 to 4. So I put in the top number first. So I have negative 1/4 minus negative 1, and that equals 3/4, which is in fact smaller than ln of 4, which was more than 1. So I get a smaller area here. Yeah, so in general, if you have a denominator, you're going to change the exponent to a negative exponent, just like a derivative. But be aware that that does not work for 1 over x. If I try to do that for 1 over x and write integral for 1 to 4 of x to the negative 1 dx, so if I try to raise the exponent 1 and divide by the new exponent, all right, that's undefined. Does not work. So that exponent rule only works if the exponent is not negative 1. But it works for any other real exponent at all. Just doesn't work for x to x to the negative 1. So you want to remember if I have x to the negative 1, also known as 1 over x, I'm going to use ln of absolute value of x. But if I have any other negative or positive or fractional exponent of x, then I can just use the power rule. All right, so for example, on this one, here's the nice picture for the square root of x. We're going from 1 to 4. What's that area going to be? So I have to rewrite this just like doing a derivative. I'm going to rewrite that root as a fractional exponent. All right, I'm going to raise the exponent 1 and divide by the new exponent. It's a little awkward, but there's sort of a shortcut you can get used to taking right away, which is to flip this fraction over and put it in the front. That's sort of what most people are going to do right away once you get good at this. But for now, I just raise the exponent 1, divide by the new exponent. Okay, so then I have, so this one looks like it might take a little more work. I have to plug in the 4 first, so I'm going to have 2/3 times 4 to the 3/2, and then minus 2/3 times 1 to the 3/2 power. Okay, 4 to the 3/2 power, square root of 4 is 2, 2 cubed is 8, so this is 16/3. 16/3 minus, this is going to be 1, so minus 2/3, so it equals 14/3, also known as 4 and 2/3. Yeah, that's that one. Let me just try and segregate these out a little bit. See where one thing begins and the other ends. All right. Now, this time, so last time I did integral of cosine, I had some negative area, so I ended up with 0 for a value. This time, I've kept the positive area, and it's very curious what that area is. So the antiderivative of cosine is sine, right? Because the derivative of sine is cosine. So an annoying thing, the derivative of sine is cosine, the derivative of cosine is negative sine. But the antiderivative of sine is negative cosine, and the antiderivative of cosine is sine. So the sine change switches function for antiderivative as opposed to derivative, which kind of makes sense, but it's annoying anyway. 0 to pi over 2, plug in the top, I have sine of pi over 2 minus the bottom, which is sine of 0. So that is 1 minus 0 is 1. To me, one of the most remarkable results of all this stuff is that this area from 0 to pi over 2 in the sine graph, or that's the cosine graph, is 1. It's the same as if I had a, so let me sketch this out a little bit. Here's pi over 2. Here's 1. All right, here's how cosine really looks. That has the same area. This curve has the same area as if I did a square that was 1 by 1. They have the same area. Isn't that bizarre? It's bizarre, but it's a fact. And then, so, that's true of all of it. Like if you do sine from 0 to 2 pi, from 0 to pi, right, these segments are all congruent. So this area is going to be 2. It's a pretty weird, interesting result. All right. What we're going to do next is we're going to start looking at your homework. I'm going to go ahead and let you know that our homework on this is going to be in your book, Chapter 5, page 303, number 27 through 47, the odds. Okay? I'm going to go through and do a couple even ones just for more demonstrations. If you want, you can just launch right into this and then watch the next video if you feel it's necessary.